So welcome everyone to Hing Ong's Dissertation Defense. Hing came to us with a Master of Science degree from Taiwan, and he didn't start out initially in my group. I knew of him only from his application, original application to the department, and just before he started, in my group, I woke up around 2 a.m. with my phone buzzing me for incoming emails. And I don't always look at these, but I popped up and turned it on, curious, and I found him asking me to advise him on his PhD in tropical large-scale dynamics. And at the time, as I say, I didn't know him very well, but I'd seen his application and I knew he was a fantastic student with a great record. And I just, in the months following, Hing was, I think, the fastest student I've ever had in terms of turning out papers from the start of joining the research group. He, as I say, he did have a master's degree to start with, but he's always been quick study and works really hard, oftentimes in the middle of the night, to get things done. So it's the first time we've done dissertation defenses in this way. The first part is, as it's always been, the public portion. Hing will provide his presentation for us, and I ask that you please hold your questions until the end. If you have questions that are brief clarifications, then you address them to me in the chat. And so I'll be able to take a look at them and then assess whether either I can respond myself with a quick clarification, or suggest that you wait to the end, or I will step in for a moment and ask Hing to address the question, depending on the nature of it. Please, if you can, wait till the very end with those. So we plan on the presentation taking roughly 45 minutes. We'll have about 15 minutes of questions from the public, after which we'll dismiss everyone but the committee. The committee consists of myself, Brian Rose, Rob Favell, and our visitor from NCAR, Bill Skamrock. And we especially appreciate his participation here. And with that, we'll let you take off.
Thank you, Paul. It's my pleasure to present my dissertation on the significance of the non-traditional Coriolis terms in tropical large-scale dynamics. For those calling in while viewing my offline slides, I will say the present slide numbers out loud. Slide number 2. Like many other atmospheric scientists, I used to believe that in our weather and climate models, large-scale dynamics are well represented because we build our models upon equations known to govern the motion of large-scale flow. And what needs improvement is to represent how the statistics of physical processes respond and feedback to large-scale flow. For example, we need to improve convective parameterization, which represent the statistics of convective processes. So I used to study convective parameterization, and I had a paper published about it 3 years ago. That was right before I came to SUNY Albany. However, 2 years ago, when I was looking for a new research topic, I reconsidered this question. Are large-scale atmospheric dynamics well represented in our models? The result of this dissertation suggests, slide number 3, no. because the non-traditional Coriolis terms are omitted in most of the current global atmospheric models. The non-traditional Coriolis terms are terms in the momentum equation that turn eastward motion upward and upward motion westward, and vice versa. They are usually omitted. However, this dissertation and a few previous papers suggest that the non-traditional Coriolis terms are considerable in tropical large-scale dynamics in terms of these three aspects. Flow response to heat sources. Second, hypsometric relation or pressure-height relation. Third, equatorial wave propagation mechanism. The results encourage restoring the non-traditional Coriolis terms into the models for more accurate simulations of MJO, the Madden Julian oscillation, CCEWs, the convectively coupled equatorial waves, and flow response by the ITCZ. No, flow forced by the ITCZ, the intertropical convergence zone. You may wonder what made me consider such a question. Slide number 4. I started from examining the equations. What's shown here are the fully non-hydrostatic momentum equations used by only few models, including UK Met Office's unified model, Japanese NICOM, and US Navy's NUMA. The yellow terms here, are the non-traditional Coriolis terms. They have a factor of 2 omega cosine latitude, which is associated with the meridional projection of planetary vorticity, and they are maximized at the equator. Then, slide number 5. These are the quasi-hydrostatic momentum equations used by earlier generations of UK Met Office's unified model. Compare slide number 4 and 5. The quasi-hydrostatic equations omit the vertical acceleration terms, which makes sense because in 1995, White and Bromley's scale analysis suggests that the vertical acceleration term is the smallest term in the vertical momentum equation for large-scale flow. Then, slide number 6. These are the hydrostatic primitive equation used by most of the current global atmospheric models. Compare slide number 5 and 6. Notice first here and here. Note that the vertical momentum equation reduces to the hydrostatic equation, while one of the non-traditional Coriolis terms is omitted. Then the other non-traditional Coriolis term in the zonal momentum equation here must be omitted for energy conservation. So to use the hydrostatic approximation is one of the reasons that people omit the non-traditional Coriolis terms, which makes sense because the balance between the perturbation pressure gradient and the buoyancy is the leading order balance in the vertical. So far, everything makes sense. Slide number 7. These are the non-hydrostatic primitive equations used by many models on the pathway toward relaxing the hydrostatic approximation. Compare slide number 6 and 7. Vertical acceleration term is restored, but the non-traditional Coriolis terms are not. So, slide number 8. According to a scale analysis, vertical acceleration term is far smaller than the vertical non-traditional Coriolis term for horizontal for a horizontal length scale of 100 kilometers or larger. However, in many models on the pathway toward relaxing the hydrostatic approximation, the vertical acceleration term is included while the non-traditional Coriolis terms are omitted. This inconsistency motivates me to ask this question. Is there insufficiency in omitting the non-traditional Coriolis terms? Before I move on, I reviewed some papers. Slide number 9. The general idea of these papers is to compare the non-traditional Coriolis terms to the leading order terms for scale analyses, and to compare biases due to omitting the non-traditional Coriolis terms to results with or without the non-traditional Coriolis term for model simulations. For tropical diabatic forced large-scale flow, White and Brownlee's scale analyses suggest that the non-traditional Coriolis terms are 10% of the leading order terms, which are the traditional Coriolis in the zonal and the buoyancy in the vertical. Hayashi and Ito's linear force dissipative model simulation suggests that the non-traditional Coriolis terms contribute 10% of the resulting wind and pressure. Hayashi and Ito's force, so in their paper, they forced the model by a prescribed heat source that propagate eastward along the equator in an intraseasonal timescale. Accordingly, slide number 10, in this dissertation, I further addressed these 3 questions. In chapter 2, how do the non-traditional Coriolis terms affect flow response to heat sources? In chapter 3, how do the non-traditional Coriolis terms affect hypsometric relation or the pressure-height relation? In chapter 4, how do the non-traditional Coriolis terms affect equatorial wave propagation mechanism? I'll first show the flow response, slide number 11. I formulated a linear force dissipative model that can switch the non-traditional Coriolis terms on and off, which is similar to Hayashi and Ito's model. I forced the model with an ITCZ-like heat source, which is steady and zonally symmetric. And because it is steady and zonally symmetric, I am allowed to make my model simpler than Hayashi and Ito's model. And here shows the meridional vertical distribution of meridional velocity contoured and vertical velocity shaded. As a sanity check, the vertical velocity is nearly proportional to the prescribed heating rate. So I put my heating rate here, prescribed. And there is an in, up, out, Hadley-like circulation. Then slide number 12. Here shows the meridional vertical distribution of zonal velocity with the non-traditional Coriolis terms contoured. So there are subtropical jet maxima here and here, associated with the Hadley-like circulation. The shading denotes zonal velocity difference without the non-traditional Coriolis terms minus width. So the shading can be interpreted as a bias due to omitting the non-traditional Coriolis terms. Compare slide number 11 to 12. We see that the westerly wind bias is located in the heating region, while the subtropical jet is not affected. This westerly wind bias here is due to lack of westward non-traditional Coriolis terms associated with heating-induced upward motion. I'd like to re-emphasize that the heat source is prescribed. In this case, the ITCZ width is 1,000 kilometers, and the ITCZ location is 600 kilometers from the equator. If we divide the maximum westerly bias by the maximum westerly wind in the subtropical jet as a normalization, we get 12% of bias. Furthermore, slide number 13. How does the normalized wind bias change with the prescribed ITCZ configuration? Here, the normalized wind bias is plotted on the parameter space of ITCZ width and ITCZ location from the equator. The plus sign here. The plus sign here denotes what I just showed, 1,000 kilometers wide and 600 kilometers from the equator. And the normalized wind bias increases when the ITCZ is narrower or closer to the equator. Inspired by these results, slide number 14. How hydrostatic is ITCZ-forced flow? The traditional measure here to validate the hydrostatic approximation is to compare the vertical acceleration term to the buoyancy term. The scale analysis suggests that the ratio is d squared over L squared, where d denotes characteristic depth and L denotes characteristic width. This ratio is very small for typical ITCZ, which suggests that ITCZ force flow is in hydrostatic balance. However, the hydrostatic approximation not only omits the vertical acceleration term, but also omits the non-traditional Coriolis terms. So an alternative measure for a tropical atmosphere is to compare the non-traditional Coriolis terms to the traditional Coriolis in the zonal momentum equation. The scale analysis suggests that the ratio is AD over YL, where A denotes planetary radius and Y denotes distance from the equator to the subtropical jet. For a non-zero Y, we don't consider any jet at the equator. This ratio can be used to explain why the normalized wind bias increases when the ITCZ is narrower or closer to the equator. And it is on the order of 10% for typical ITCZ, which suggests that the hydrostatic approximation is associated with 10% of bias in ITCZ forced flow. Okay, slide number 15. We've talked about how the non-traditional Coriolis terms affect the flow response to heat sources. Note that I prescribed the heat source as if I knew the distribution of the heating rate. In reality, the heating distribution is difficult to simulate. However, even if we had the perfect representation of the statistics of the physical processes which simulate the evolution of the heat source perfectly, the forced flow would still be substantially biased if the non-traditional Coriolis terms are omitted. With that in mind, let's move on to the hypsometric relation, or the pressure height relation. Slide number 16. I'll start with a schematic. Consider a zonal vertical space. Given the pressure at the sea surface, we can estimate the height of pressure level aloft. As a simple demonstration, If the density is horizontally homogeneous, the hydrostatic balance would suggest a flat isobaric surface aloft. Then, the quasi-hydrostatic balance further introduces the non-traditional Coriolis term as a correction to gravity. Westerly winds are associated with upward non-traditional Coriolis term, which effectively makes the air lighter, so it needs a greater thickness between pressure surfaces to balance. The opposite is true for easterly winds. Then slide number 17. Here is the corrected hypsometric equation. Most of it is the same as the traditional hypsometric equation. It means that the thickness between two pressure levels, P2 and P1, equals to the integral of gas constant R times virtual temperature TV divided by gravity. But the gravity has a correction factor 1 plus A, where the correction A includes the non-traditional Coriolis term, and it's so-called the Utrecht effect. The two non-traditional metric terms here are included for completeness, but they don't make a noticeable difference. I calculated the height of pressure levels using this equation with and without the correction A, using more than 300,000 selected tropical rawinsonde profiles. And here, slide number 18 shows some of the results. The figure shows the probability density of all available data points. The vertical axis denotes the bias of height due to omitting the non-traditional correction at 500 hectopascal. In terms of one standard deviation, the range of height bias is roughly between 0 and half a meter. And the height bias at 500 hectopascal is negatively correlated with the zonal wind at 700 hectopascal, which is plotted on the horizontal axis. With the linear regression, an easterly wind of 8 meters per second is associated with the positive height bias of half a meter, which is consistent with the schematic in slide number 16. Here is the easterly wind, and above that is the quasi-hydrostatic height, and the hydrostatic approximation overestimate the height. Back to slide number 18. And let's compare the height bias to the height variability. We use the ERA interim data in the tropical region and filtered for wave number 1 to 10. And the horizontal standard deviation is roughly 10 meters at 500 hectopascal. So the height bias is on the order of 5% of height variability. Although such a height bias may be smaller than random error in height estimation with rawinsonde, it points out the source of systematic bias in model initial conditions. Then, slide number 19. Showing that both the vertical non-traditional Coriolis term and the buoyancy are contributors to thickness between pressure levels. Here show the zonal vertical distribution of these two contributors to the variability of thickness associated with the MJO. The vertical non-traditional Coriolis terms are contoured and the buoyancy is shaded. These are calculated from the ERA interim data and are regressed upon MJO filtered tropical rainfall at 90 degrees east which is marked with the green arrow here. On the west side of the green arrow, which is in the rear flank of the active MJO, there is a region dominated by upward non-traditional Coriolis term with weak buoyancy signals. On the east side, which is in the forward flank of the active MJO, there is a region dominated by positive buoyancy, slightly offset by downward non-traditional Coriolis term. In terms of the maxima of absolute values, the vertical non-traditional Coriolis term is roughly 5% of the buoyancy. Okay, slide number 20. We've talked about how the non-traditional Coriolis term affect hypsometric relation. Note that I use surface pressure as a lower bound for upward integration because I used rawinsonde data. For model data assimilation, however, such a reliable reference level does not exist. So a thickness bias can contribute to height bias above or below. Also note that the random error in rawinsonde observation may be larger than the systematic bias here. However, even if the wind, pressure, temperature, and moisture contents are all perfectly observed, the assimilated height will still be substantially biased if the non-traditional Coriolis terms are omitted. With that in mind, let's move on to the equatorial wave propagation mechanism. Slide number 21. I'll start with the structure of an analytical solution of a wave. Here shows the zonal vertical distribution of its mass stream function along the equator. In the tropical atmosphere, adiabatic warming or cooling is usually partially offset by diabatic cooling or heating, which reduces the buoyancy generated. Let's first consider an extreme case where adiabatic and diabatic effects completely offset each other, leaving no buoyancy. Under such circumstances, will these circulations propagate? The normal answer is no, because no buoyancy means no gravity waves. However, we can see another wave propagation mechanism if we take both the non-traditional Coriolis terms and the vertically decreasing density into account. The shading here denotes meridional planetary vorticity divided by density, or 2 omega over rho. The compressional beta effect is a vertical advection of the shaded quantity, and it transmits these circulations eastward. For example, the circulation in the middle is associated with positive meridional vorticity, which points into the screen. And the downward motion on the east side yields positive advection of the shaded quantity, which increases the meridional vorticity on the east side. The opposite is true for the west side. So the circulation propagates to the east. Then, slide number 22. Compressional beta effect is first described in the paper by Verhoeven and Stelmach, who derived the compressional Rossby wave solutions on an XZ plane with a mistake in their derivation. This study corrects the mistake and further expand the spatial domain to a 3-dimensional equatorial beta plane. Theories about waves on an equatorial beta plane have a long history. Matsuno derived the solutions with the shallow water model. In Holton and Hakim's textbook, we can find the solutions with an inelastic model, but without the non-traditional Coriolis term. Bruman, as well as Roundy and Jeniga, derived the solutions with the non-traditional Coriolis terms, but with a Boussinesque model. None of these studies found the compressional beta effect because it needs both the non-traditional Coriolis terms and the vertically decreasing density. And the present study accounts for both of these ingredients. In addition, in my derivation, I put a factor alpha in the adiabatic term in the thermodynamic equation. Alpha equals to 1 means dry adiabatic. Alpha between 0 and 1 means partial offset of adiabatic effects by diabatic effects, where buoyancy frequency is effectively reduced. Alpha equals to 0 means complete offset or effectively neutral. Then, slide number 23. Here shows the dispersion relations on the wave number frequency space for a strongly stable atmosphere where the effective buoyancy frequency is far larger than the meridional planetary vorticity. Curves on the right side denotes eastward propagating waves and left side denotes westward propagation. For the same wave number, a higher frequency means faster phase speed. In the strongly stable case, my solution is like the Matsuno solution, and you cannot distinguish the black and red curves, where black denotes with the non-traditional Coriolis terms and red without. Now, watch and listen to this video. The sound frequency played here is proportional to the effective buoyancy frequency used to plot each frame of the animation. Please pay attention to the frequency axis and the separation of black and red curves. Let's watch again. With the effective buoyancy frequency decreasing, the phase speed also decreases. As you can see, the frequency or axis shrinks. And the solution with and without the non-traditional Coriolis terms separate farther, while the effective buoyancy frequency is decreasing. In the last frame, it is effectively neutral, and the solutions without the non-traditional Coriolis terms no longer exist. But we still find solutions with the non-traditional Coriolis terms. And this is the compressional Rossby wave solution, which propagates eastward at a phase speed of 1/4 meter per second. Then slide number 24. No. Slide number 24. This is a new figure created yesterday. The compressional beta effect can serve as a contributor to the eastward propagation of MJO. Here shows the zonal vertical distribution of the compressional beta effect, which is contoured, and the local tendency of meridional vorticity shaded. These are calculated from the ERA interim data and are regressed upon MJO filtered tropical rainfall at 90° east. which is marked with the green arrow. In the mid-upper troposphere, in the MJO active region over the arrow and around this region, the meridional vorticity is decreasing as you see the dashed contours. Or in other words, the vertical wind shear is changing toward easterly. Meanwhile, in the same region, the upward motion in the active MJO yields negative advection of planetary vorticity divided by density. In other words, there's a negative compressional beta effect. In terms of the minimum value, negative values, the compressional beta effect contribute 11% of the meridional vorticity tendency associated with the MJO. In summary, slide number 25, in linear models, the non-traditional Coriolis terms affect the flow response to heat sources by roughly 10%, and the hypsometric relation by roughly 5%, and the equatorial wave phase speed by roughly a quarter meter per second, or the meridional vorticity tendency associated with MJO by roughly 10%. Unlike many numerical errors in the models, these effects don't start small and grow large with the time integration. Instead, omitting these effects biases the initial pressure-height relation and biases the zonal wind and wave propagation every time step. These biases may grow even larger if nonlinear processes are considered, which is left for future study. These results encourage restoring the non-traditional Coriolis terms into the models for more accurate simulations for MJO, CCEWs, and ITCZ-forced flow. This restoration is not going to resolve all the problems, and the importance of improving the representation of physical processes is not downgraded. However, the restoration of the non-traditional Coriolis terms should be among the top priority of model development, because all other parts of the development depend on the choice of governing equations. And to validate the implementation of the non-traditional Coriolis terms, the compressional Rossby wave test can be used as a benchmark. Slide number 26. This test aims to push the dry dynamical parameters to a limit that is relevant to moist physics, but difficult to test without modeling the moist physics. Accordingly, I used 3 special treatments: equatorial F-plane, fast planetary rotation, and barotropic gas. I included the non-traditional Coriolis terms into the MPAS atmospheric dynamical core and used the upgraded dynamical core to simulate the compressional Rossby waves. And the animation you see here shows the results. The numerical solution in green contours overlaps the analytical solution in black contours. So you can really distinguish the 2 types of contours, which validates the implementation of the non-traditional Coriolis terms. For the future, slide number 27, I have a proposal titled Effects of the Non-Traditional Coriolis Terms in Atmospheric Models. It aims to explore possible nonlinear effects and possible linkage to biases in ITCZ configuration and MJO propagation. I plan to assist the inclusion of the non-traditional Coriolis terms into the NOAA FV3 model. It may lead the modeling community to a new era where people build their models upon a sufficiently accurate governing equation. With this proposal, I was awarded the NOAA Climate and Global Change Postdoctoral Fellowship, but I declined this award because it doesn't allow bringing the fellowship to an institution other than the proposed one. So the proposed study is to be done at UC Davis. Finally, slide number 28, acknowledgements. This study would not have been done without my advisor, Paul Roundy. I first knew Paul by an email correspondence in 2016. That was before I attended the conference on hurricane and tropical meteorology in San Juan, Puerto Rico. Paul, as a chair of that conference, sent the attendees an email about something that I don't remember. But I still remember his email signature here. See that creature climbing on the business card. With that first impression, then 2 years ago, I asked Paul to be my advisor after I Googled the term non-traditional Coriolis terms and found Paul's paper. And this turns out to be a great decision. Paul cares for me, supports me, and guided me. Paul is also extraordinarily accessible. His office is usually open for walk-in advice, and he usually responds quickly to emails. So thank you, Paul. Slide number 29. Many thanks to my other committee members, Ryan Rose, Rob Favell, and Bill Skamrock. Their comments improved the quality of this dissertation. Bill also provided a tutorial that makes the development of the MPAS possible in this study. Many thanks to my audiences. First, thanks to those attended my defense rehearsal, Ahmed, Ajay, Xiaojun, Minghao, and Fangze. Also, thanks to those attended my prospectus defense, climate group meetings, Northeast Tropical Workshop, AMS annual meeting, and AGU fall meetings. Moreover, thanks to those attended my invited talks at UC Davis, MIT, NCAR, and Taiwanese institutions including NTU, Academia Sinica, and Central Weather Bureau. The reactions of my audiences helped me improving my presentation. Many thanks to DAES staffs, Shayna, Annie, Barb, Kevin, and Ash, for making all those administrative and technical issues so easy for me. Slide number 30. Many thanks to my former PhD advisor, Wei-Qiang Wang, for bringing me in and caring for me. Many thanks to my master's advisor at NTU, Jianming Wu and Hongji Guo, for their rigorous training in scientific writing and atmospheric dynamics. Many thanks to Marat Kairodinov for his inspiring talk on March 26, 2 years ago. Many thanks to all DAES and ASRC faculties and students for making such a friendly research environment. Many thanks to my teammates in our soccer team, Snow Squad Squad. Many thanks to my wife, Wenqi, and my children, Ik Liang, also known as Mosa, and the newborn, Ika. Slide number 31. Many thanks to those who funded me during my 3-year study. ASRC offered me the graduate fellowship in my first year. DAES has been offering me the teaching assistantship in my 2nd and 3rd year. Taiwanese Ministry of Education has been offering me the government scholarship to study abroad in my 3rd year. Paul's grant from the NSF funded my summer wages and trips to conferences. My parents and parents-in-law partially funded some of my needs, like my car and trips to Taiwan. Next slide. If you're interested in using the linear force dissipative model or the compressional Rossby weight test, please find the MATLAB script or the Fortran modules below. And that's all. Thank you.